Over the last few years, we've seen a really dramatic decline in Antarctic sea ice, a decline that's happening much faster than what we had anticipated could happen.
One way we try and convey how unusual something is with statistics. We talk about a 1 in 10 year flood or a 1 in 100 year flood. And if you run those sorts of statistics for Antarctic sea ice last year, you get a number somewhere between 1 in 7.5 million years and 1 in 7 billion years, neither of which make any sense in a record that's only 40 years long. Antarctic sea ice plays so many vital roles in the world's climate system, in the ecosystems around Antarctica, and more broadly.
The regime shift will have implications for the biology around Antarctica and in the Southern Ocean that depends on the sea ice for habitat, both on top of the sea ice and underneath the sea ice.
We saw the heartbreaking story of emperor penguin colonies where the ice melted underneath before the chicks were fully grown, and they all died.
It will also have impacts on the rest of the climate system in Antarctica, and particularly the way sea ice interacts with ocean circulation and also the stability of the ice shelves around Antarctica.
Sea ice protects the Antarctic coastline and it protects the Antarctic ice shelves. So taking away that sea ice will probably lead to a more rapid disintegration of the ice shelves, which hold back the ice on Antarctica. As that sea ice disappears, the ice shelves disappear and the ice on Antarctica flows into the ocean, accelerating sea level rise. In terms of global impacts of sea ice changes on weather, that is a scientific question that we're only just starting to unravel. There's some initial evidence suggesting that rainfall over Australia could change by 15 to 20% because of the sea ice changes. Now maybe 15% doesn't sound like much, but if you're in an area farming wheat and you only just have enough rainfall, that could be the difference between a crop that fails and a crop that you can harvest.
All of the indications seem to be pointing to this change being related to heat building up in the ocean, and we're seeing an enormous amount of heat being taken into the ocean as the climate warms.
So we know that the ocean is warming, and we know that that warming is caused by humans. We have quite strong evidence tying the ocean warming to the sea ice loss. So I would say I'm quite confident that what we're seeing is the long-term impact of human greenhouse gas emissions.
We can look at how Antarctic sea ice has behaved over the last few hundred years, and when we do that, we don't see anything that looks anything like this dramatic decline we've seen over the last decade.
It could change to become even worse again in the future. There could be another rapid decline in Antarctic sea ice, and we should do absolutely everything in our power to try and reduce the likelihood of those bad futures.
Antarctica is changing very rapidly. What we're trying to do is understand how these cracks grow and predict the timing of these big calving events that create very large icebergs.
We don't know what controls when they break off and how they break off.
We don't really understand how much sea level rise is going to be caused by ice shelves. We collect a lot of ice cores, we break it, we see how tough it is compared to other ice.
There isn't much data on that because getting access to ice from Antarctica is difficult and you have to get it halfway across the world without melting it.
Ice shelves are very important on the global scale. They are the floating parts that surrounds the margins of the continent. They hold back ice from the interior of the Antarctic continent. There's been periods where we've had sudden ice shelf collapse or loss of ice shelves. The famous one is Larsen B in the early 2000s.
We had extreme warm temperatures one year. We got a lot of melting on the surface and then a lot of fracturing, and then that ice shelf completely disappeared. It just disintegrated really rapidly. And that means that this ice that's flowing off of the continent has nothing stopping it. So that ice can just completely flow out into the sea, and it breaks up as icebergs and then just contributes to sea level rise.
Antarctica contains the biggest ice sheet in the world. It has the potential to raise sea levels by tens of meters, And we are starting to see significant contributions to sea level rise from loss of ice from Antarctica. A lot of the world's population live in coastal cities and around coasts, and so this will quickly have a direct impact on coastal ecosystems, mass migration, and for society as a whole. So Antarctica loses about half of its mass through iceberg production, through calving.
That's a very natural process, and we expect that to happen nicely, continuously. The ice shelf grows, it breaks off, continues to grow again. But we're seeing that this process is actually being changed by the climate, and we want to understand what's happening there.
The big changes that have been happening are mostly in West Antarctica, so areas like Thwaites and Pine Island. The ocean is warming and a lot of the ice shelves are melting and thinning, and that is reducing their buttressing power. The effect of calving is less well understood. I work on the Brunt Ice Shelf, where we have the Halley Research Station. We are interested in the different drivers of crack growth. So this particular ice shelf has a number of active cracks within it. So it's a dynamic ice shelf. It moves about 4 meters a day, which is relatively fast. But also it's had these what we call rifts, which is a full thickness crack that goes right through the ice shelf, and have led to several large calving events in the last 4 years.
The Rift Tip project is about trying to understand the rate and timing of why ice fractures and why we get these large icebergs produced from ice shelves. Iceberg A81 was formed from Chasm 1. Chasm 1 was this large rift that we expected to form at some point. The ice shelf had got as big as we knew it had got before, and then that crack eventually propagated through the ice shelf, and then the iceberg broke off. The other crack was aptly named Halloween crack because it was found on Halloween. And this grew really quickly, and it was less expected, and led to us realizing that maybe the way this process happened, we don't understand as well as we should. So if we can't understand how and when ice fractures and produces icebergs, we don't really understand how much sea level rise is going to be caused by ice shelves. The first time I saw Halloween crack, we were flying towards Halley Station out of the little twin otter plane, and you see this large opening and you just go, wow, it's huge. It's open water, this vast expanse that if you were on one side of it, you could be convinced that maybe it's just sea and that there's not ice on the other side of it. But as you fly over the crack, the further and further you get towards the tip of it, it just gets narrower and narrower. And then we landed in the plane to do some surveys around the very tip of Halloween crack, and all that remained was this very, very tiny hairline little fracture in the surface of the snow. And myself and the field guide were walking along tied up with a bamboo stick trying to find where this crack was. And that's in sort of 50 kilometers that the crack has gone from this massive, massive thing to just this tiny little hairline fracture that you can hardly even see.
What the whole project is designed to do is fill in the gaps between understanding what's happening at the small scale with crack growth and the large scale with iceberg production.
We think it all comes down to sort of centimetre, millimetre ice crystal scale of where that crack goes. It's such a small process that we're trying to understand with all this large equipment and these large expeditions.
The main thing that we're doing here is joining all these things together on a specific crack, on a specific ice shelf, and so we're getting a full view of everything from the micro scale to the wider impact on the actual iceberg formation. Our research station Halley is down here. The area we've been working in 24-25 season is up here at the tip of Halloween crack. So this is about a 50-kilometer drive. The crack has been growing since 2013. We've been monitoring its width very closely. We've been monitoring strain rates around the tip of that crack. And more recently, we've set up seismometers around that crack. It is quite amazing what we can do with the satellite imagery these days to understand how cracks are growing, but it doesn't tell us about what's happening in the subsurface. For that, we've been using radar measurements, so driving a skidoo with a radar system towed behind, which can image the properties of the ice at depth. We can also use that to find cracks that are not necessarily visible at the surface.
In Antarctica, we actually see quite different characteristics of this fracturing, whether that's on the Brunt Ice Shelf, where I've been to, or Larsen Sea Ice Shelf, kind of tends to do the complete opposite of what we'd expect. We want to understand why it is that when ice fractures, it goes through certain types of ice more so than other types of ice. So I use geophysics to try to do that. The previous season, I'd gone over to this bit of ice and installed 2 instruments that were there to track if the ice did break off. And then we turned up this year and they're just gone. The ice is gone, the instruments are gone, and you have this real understanding of the scale of what we're studying. We also collect lots of ice cores where we're really looking at the very small scale properties. So we drill down to over 130 metres and we roughly recover a core every 80 to 90 centimetres.
When we're in the field and drilling the ice, it's quite a exciting process.
We need the cores to be in a real pristine condition. They can't have any fractures or anything in them that we've created. You obviously accidentally drop a couple and theoretically they're worth about £8,000 per metre is the price that BAS puts on them.
The ice has to be taken back to Halley. Then at the end of the season it was collected and then loaded onto the Sir David Attenborough ship.
It's a long process, so we had to wait around 9 months to see the ice again.
That's quite a nervous process. When it arrives here, you want to make sure that it's still in the same shape that it was when we originally logged it.
The ice is just moved in a regular freezer van. Often the driver will ask us what we're transporting and is always quite excited when they hear that it's ice from Antarctica. Relief when you finally get your hands on them. You often get very friendly people wanting to help carry the boxes off of the lorry with no grace and decorum, and you're sat there thinking they've made it this far, not broken, please, we don't want them broken. We pick and choose the cores that we want. We then use this scanner here where we're able to take a really high resolution photograph of the cores, and from that we can look at whether or not there's any ice or features in the core that we can't necessarily see with our eyes. And then we take the cores through to the other freezer where we cut and prep them, and that's where we do all our analysis. This is one of our really hard continental ice, bits of ice that is really uniform, like really uniform bubbles, really strong. Really old. The smaller the bubbles, the older the ice tends to be. And that's why people use it for chemical analysis, because any sort of bubbles that are trapped inside it still preserve the conditions of the climate at the time that they were trapped. This one is around 128 metres deep from the ice shelf. And then as we melt it, we'll see what's going on inside the ice and the bubbles. We think from the size of the bubbles, it could be anything from sort of 100,000 years old to 500,000 years old, which for ice is not that old. This ice was formed somewhere way inland on the continent of Antarctica and has then eventually flown off into the ice shelf. So if you melt this ice, you'll hear it bubbling. As the little bubbles inside, the change in air pressure, they release. We melt it in the freezer, and as we're melting it, we're able to extract the gases off of the core, and we're also able to keep the liquids. We can look at different types of chemistry that could be to do with the amount of sea ice that was present in Antarctica at that time of year. It could be to do with volcanic activity, and we use all that to both understand the chemistry of the climate in the past, but also age our ice. So without that, we haven't really got a good understanding of how old the ice is that we're studying.
What we don't really have at the British Antarctic Survey is a capability to do physical property analysis of ice.
The BAS team reached out to us with our long-standing history of working on ice. I'm particularly interested in how geomaterials deform full stop, and understanding ice is a very similar problem to rocks, just under different conditions and different style. Well, we have 5 ice labs. We have a lot of equipment built by our excellent engineers here at UCL, and we can squash things, and I'm excited to squash anything. You give it to me and we'll squash it. Here the problem is coming up with some experiments where you can actually measure in a controlled environment the strength of ice in the context of the ice shelf that they're working on. If you have a large fracture that goes from top to bottom of the ice sheet, you're going through this material. Just like if you're tearing a piece of paper or tearing a piece of card, you need to know if you're tearing card or paper, because one's going to be easier than the other, and that will control where the fracture goes. The idea here was to actually get core and actually bring it here and test that under some very controlled temperature conditions, controlled rates and speeds. How does the ice fracture as a function of depth? Well, it's pretty exciting, you know, having a freezer full of ice that has come from Antarctica. Significant amount of field work has gone on and logistics to get it from where it was drilled to bring it here. I certainly lose sleep on whether this stuff will melt. That's for sure. I wake up in a hot sweat. What controls the strength of a material is the things that are within it. So many things that are crystalline essentially have a grain size. And the grain size is a primary control on how things break. On ice, we have to look at that under the microscope because these grains are really small. And to do that, we make a thin section.
We essentially take a really thin piece of ice, glue it to a piece of glass using just cold water, and then file it down until it's 1 grain thick. And then we can use polarized light to see the orientation of the crystals, the size of the crystals, and that tells us about whether or not there's been any sort of stress on the ice that could have made those crystals grow in a certain direction, whether or not the fracture has maybe pushed the crystals into a sort of direction. It also tells us maybe about how long the ice took to grow, if it's melt, if it's fresh snow, if it's old. So we can learn quite a lot from the crystal structure. This is ice from quite shallow on the ice shelf, maybe around like 15 meters. And it's got this really, really clear ice that would have been formed when there was melt at the surface, and it's percolated into the ice shelf and then refrozen at a later date. So we're gonna look at what's inside it. So this is just a light board, and this is just polarized paper. When we look at the sample at the moment, it just looks like regular ice. This is our melt, and this is our firn, our shallow snow. And then when we put the polarized paper on, we can really clearly see the crystals. So our melt has really, really quite big crystals, these bits here. And then the firn in between, this like almost snow transitioning into ice, doesn't really have large crystals at the moment. It's pretty fresh, pretty shallow, pretty new. Hasn't had time to grow into any sort of large crystal at the moment. This is one of our samples from a little bit deeper down, where we've got our firn and then our melt.
It looks really nice.
It looks like magic, doesn't it?
And that's very useful because it allows us to tell us things about the orientation of the crystals and how they were formed. And if, for example, they were stressed, also the changes in colours would be representative of that as well.
Because we see completely different colours, it actually means that there's probably been no stress acted on it, that all the grains are completely randomly orientated. If they were all pink or all green, then they'd all be facing the same direction, which means that something has made them form in that way or made them move in that way.
Random scattering of crystals is actually the most common thing. So that's what we'd expect it to look like. If there had been some sort of structure in the ice, then we would think that there's some sort of stress acting on the ice shelf to push the crystals into a certain orientation, or it's that the fracture, the tip of the fracture, is actually causing the crystals to change orientation.
What we then do is test how does the ice fracture as a function of depth under some very controlled temperature conditions, controlled rates and speeds. We have to prepare samples, shot the core up to make semicircles. So what we've got here is a hydraulic press and I can put about 1 ton of load maximum on a sample. We're not going to need to use anywhere near that for the ice. It's much, much weaker. But it's been custom designed and assembly to essentially load our sample. There's 2 rollers here and here, and then we'll slowly increase at a control rate, the piston coming down, and it will increase the stress until it breaks. In here is a load cell. This measures and sends a signal back to the computer telling us exactly what the load is. What we've also got is a high-speed camera that's set to record at about 18,000 frames per second that should show us the fracture propagating. You can see here the sample, zoom in. We're going to load this down. It's going to come down. What we're hopefully going to see is that fracture propagate across. 0.01 millimeters per second is what we're going to bring that down at. Consistently start.
Start experiment.
This is the distance going down, so that's 18.7 millimeters. You see we're now at 18.5 millimeters, so let's move 0.2 of a millimeter. So we're waiting for essentially a kick in the stress. There we go. And we're starting to load the sample now. It's going up nicely. Oh, no. Increasing stress. Beautiful signal there. Great. That was a really nice one.
So this is the fractured surface of the ice that we've just broken through. So we'll measure the length of that edge and then use that to calculate the fracture toughness.
So this is the background levels where there was no load on the sample. And as the piston came down, you can see that there's a load being increased. It's non-linear because ice has cracks in it. And you see a nice linear elastic phase here, and then you can see stress build up, and then you see there's a crack and there's a stress drop. But we've certainly, in previous cores that we've experimented on from this batch, we've had samples much, much weaker and samples much, much stronger, which clearly relate to the microstructures. And what you can see is that the fracture's there. If I go forward 1 frame, the fracture's here. So it's moved from here, which is about 1 centimeter, and on the next frame, it's moved from there. So it's moved about 1 centimeter in 1/18,000th of a second. You're talking about rupture tip speeds there of approaching 1 kilometer per second. So really, really fast. We're actually finding that the weak firn snow is surprisingly stronger than previously thought. There are lots of assumptions in the literature that this stuff is actually quite weak. We're actually seeing that the shallow snow is actually a lot stronger. In particular, we're finding these melt layers are much stronger. Nobody has measured that, to my knowledge, the strength of these layers so far. So there's clearly different aspects of the ice structure, some things that we know and some things that are completely new in terms of variations of strength. We are systematically going down through all of the ice, measuring a variety of different parameters, which is really going to help us in terms of feeding that into the larger scale models.
We're essentially getting the missing pieces of the puzzle to understand what's quite a complicated dynamic evolution of the ice shelf over the last 10 years. This is some kind of example of our model output. This is in just a 2-dimensional form of the front of an ice shelf, where the colors represent the stress with depth, and this dark area is a representation of an area where a crack has appeared. This shows how over time the crack evolves and the stress near the crack tip evolves, and once it exceeds a certain threshold, the crack can penetrate all the way through the ice and the calving event happens. And so what we can see with our new model is a time scale for when a new ice front appears, how long it takes to create enough stress that will create a new crack and another calving event. So that's kind of an exciting point that we've got to with the model so far. We can run the model forward in a kind of predictive way and find out what the future behavior of this particular ice shelf will be. Somewhere like Thwaites Glacier, where we're seeing some of the biggest impacts of climate change, the cracks in that area are less well understood and it's much more difficult to work there. It's harder to access and it's more dangerous because the ice is moving more quickly. The work we're doing and the models that we're producing will be applicable to areas like Thwaites and the rest of the Antarctic margin.
We need to do this research. We have to go to Antarctica and collect this data and model Antarctica to be able to understand how it's changing and really reduce our uncertainty in how that's happening, to have an impact and make a change.
We want to give policymakers the information that they need. To some extent, it's frustrating that not enough is being done about it from the policy side. I do feel like doing the science is important, and there's a range of sea level rise, but it's all higher than it currently is. We need to be as certain about numbers that we're providing, such that there's no excuse not to do anything, because this is very certain. We can tell you with confidence that this is how things are going to go.
To me, this is my first entry into an area where I feel I can genuinely provide some expertise that will help to something that is really important, fundamentally important for the future of humans and the Earth. And if I can provide laboratory data easily that will help researchers, then that's as exciting as it gets.
It's like nowhere else you will ever go, and you're there and it's so quiet and so beautiful. The sky is so blue often, it's like a real blue that you don't get to see anywhere else, and it's just, really magical.
You would think that the excitement of going would fade over time, but for me it doesn't really. It's a beautiful place, and it's a shame to see it changing so quickly.
We're going to start, though, with a special report on Antarctica. Sometimes climate change news, it can all be a bit drip, blurs into one, just overwhelming and depressing. And it can be hard to tease out those stories that really, you have to sit up and listen to, really. But this is one of those. Our Australia reporter, James Woodford, he's been in Hobart, Tasmania, with nearly 500 researchers for a conference that was billed as an emergency summit for the future of the Antarctic. Rowan caught up with him to hear all about it.
James, I want to hear about the general vibe at the meeting. But first, there was one statistic that really captured everyone's attention there. And for you were saying this captured the seriousness of the entire climate crisis.
Yeah, thanks, Rowan. Look, the mood at the conference, at the summit, was definitely somber, and at times just everybody just trying to make sense of the enormous changes that are taking place down in the Antarctic. And normally statistics can make people feel pretty sleepy. So bear with me on this one. As many listeners will be aware, there was a precipitous drop-off in the extent of the winter sea ice around Antarctica in 2023 and again in 2024. 2024 was nearly as bad as 2023, and in 2023, there was 1.55 million square kilometres below the expected average extent of sea ice, which was the lowest recorded since satellite data. That's, just to give some context, that's an area 6 times the size of the United Kingdom. It's just an enormous area. I think everyone was pretty alarmed by that, but now researchers have calculated just how incredibly dramatic that collapse in sea ice actually was. Nerily Abram from the Australian National University, she told the summit this was 7 standard deviations off the mean for what the extent of sea ice should have been. This means we're not talking about a 1 in 10 year event or a 1 in 100 year flood. This was an event that models would have predicted could only occur somewhere between 1 in 7.5 million years to 1 in 700 billion years.
All right, so basically impossible on a planet that's only 5 billion years old. Well, what does that mean? That's an incredible number. Is that it's obviously an outlier, but is there a mistake there? How do they explain that?
Exactly. Obviously, that kind of a number is impossible. And really, what it's a product of is that no one could have foreseen that Antarctic sea ice would have dropped off a cliff in the way that it has. Abrams says that in just a decade, the decrease in the Antarctic is equivalent to that lost in the entire Northern Hemisphere in the past 45 years. Even more alarming is the projection that Antarctica could possibly experience summers that are essentially free of sea ice before even the Arctic, which is projected
Wow.
to reach that point sometime before 2050.
Wow, I think we're up in the Northern Hemisphere here. We're much more aware of the problems in the Arctic, and a phrase I often use is, "What happens in the Arctic doesn't stay in the Arctic." In other words, if we lose the summer sea ice in the Arctic, it has these huge knock-on effects, and so I take it it's the same in the Antarctic.
Yeah, exactly. As we're starting to learn with the Northern Hemisphere, with some of the changes in the ocean currents, some of the very similar things are starting to take place in the Antarctic. And I wish I could just say to you that this drop off in sea ice in the Antarctic was only of academic interest. But unfortunately, that would be a white lie. And I'm sorry, no pun intended. In fact, researchers are now scrambling to try to understand what the implications of this are. Firstly, they want to know whether this is a new normal for Antarctic sea ice. And the consensus at the conference, like every scientist that I spoke to after Abrams' presentation, said that it is unlikely that sea ice extent will return to what it was before it began to fall in 2016. But it also has these huge global scale climate and ecological consequences. For a start, having that much less ice is going to lead to much more heat being absorbed by the ocean just because it's not reflecting the sunlight back into space. And it also changes the salinity of the Southern Ocean. But perhaps the biggest worry is that the sea ice acts like a protective barrier or apron around the entire continent that stops the ice shelves on the Antarctic coastline from being buffeted by waves and exposed to more of these warm currents.
Right, so it would accelerate the ice cap itself. Did they talk about that at the conference?
Yes, they did, Rowan. There was a gripping presentation from Sarah Thompson at the University of Tasmania. She spent last summer camped on the Denman-Shackleton ice system with her team, and they were drilling through 200 meters of ice shelf to reach the ocean underneath. And her results show that for the first time, that warmer, modified circumpolar deep water is getting into the cavity under the ice shelf. And at the point where their drill hole was located, the underside of the shelf seems to be melting at a rate of about 2 meters per year. Again,
Wow.
That might sound academic, but if the Denman-Shackleton ice shelf melts, that's 1.5 meters of global sea level rise just on its own.
Wow. Well, so how are people taking this there? I mean, these are kind of these people, they're climate scientists, glaciologists, they're well aware of the problem, but was it shocking even for them?
Yes, they were really shocked by the presentations of their colleagues. And some of them said to me that after the drop-off in sea ice in 2023, that they just kind of hoped that 2024 things would bounce back. And they're definitely not confident that we're going to see any kind of a return to previous levels of Antarctic sea ice. And a summary that really has stayed with me since the conference was from Ed Doddridge, who's also from the University of Tasmania. And he summed up the disaster unfolding with just one word, and that was grim.
Okay, I thought you might say a swear word, but grim. Yeah, it is grim. James, thanks very much for reporting that.
Great. Thanks very much for having me, Ron.
Yeah, we were hearing there on a little bit about the work of Sarah Thompson. She is from the University of Tasmania. James met with her, and she was talking about the melting and all the warming going on. And while she was waiting for a flight to Antarctica, I got in touch with her and asked her to tell us a bit more about her work. And here she is.
One of the most challenging things working in East Antarctica is that we think the most significant changes are actually happening in one of the places that's most difficult to measure. And that's underneath the ice shelves, where the ice is being melted by the warmer ocean water. We know from other regions that ice shelves act a little bit like dams. If they start to weaken or break up, then ice from the continent can flow more quickly into the ocean, contributing further to sea level rise. As a whole, the region that we're currently working on holds a potential 1.5 metres in sea level rise contribution, but we don't really have a very good understanding about the rate of change or the timescales over which it might happen.
Wow, imagine working on the melting of the underside of the ice sheet.
Yeah, I know. I asked her what it's like doing that, actually, and also what it's like being a climate scientist in this period of crisis. And also I wanted to get a flavour of what it's just like being there, and that's your day job. You know, for us stuck in offices here, what's it like? And here she is.
Being able to work in this field and make a contribution, however small, to our understanding of these systems in Antarctica is such a unique opportunity. Being able to better predict the impact that they might have on our future is something that makes me hopeful. I think the more we understand, the better placed we are to face future challenges and to start to mitigate some of the changes that we see. Antarctica is an amazing and challenging environment to regularly work in, and there are moments every now and then, especially when you're out on an ice shelf for weeks at a time, and you look up and the realization of where you are and just how incredible that is hits you all over again. But I think for me, one of the really remarkable aspects of working somewhere like Antarctica is the diversity of amazing people that it attracts, all with different skills and experiences. And that's often what makes working in this kind of environment so unique.
Well, it almost makes you want to be a polar biologist. It does sound amazing. But what about the ecology of the region? What do we know about how much that's likely to change?
Yeah, well, that's a really good question. It's something I wondered about. So I hunted down another biologist, a climate change biologist, Sharon Robinson from the University of Wollongong. And she specialises in the Antarctic, been there loads of times. And this is what she said to that.
As ice retreats with global heating, areas of land are exposed and vegetation can expand and colonise these new areas. So in some areas, especially on the Antarctic Peninsula, we can see clear evidence of newly green areas. But Antarctica is essentially a desert. There isn't much snow and it hardly ever rains. Plants grow really slowly, about 1 to 3 millimetres a year in the case of the mosses. Most of the vegetation relies on the snow and ice banks to melt and provide a steady stream of water through the summer. In some areas, those snow and ice banks are disappearing or losing connectivity with the vegetation. And then we see previously gloriously green areas turning grey as they dry out. Seeing lush green areas that you've seen in the past turn grey is really sad. I really worry that we will lose some of Antarctica's rich biodiversity, like these ancient moss forests, along with the tiny animals like tardigrades or moss pignuts that live within them. Off the coast, we're losing sea ice at alarming rates. This can be catastrophic for the animals like emperor penguins that breed on the ice, and for the tiny animals on the seabed below that rely on the shade from sea ice to keep the algae from overgrowing them.
So that was good to hear tardigrades get a shout out there.
Old New Scientist favourite there, yeah.
Definitely.
It's interesting that the continent, it's sometimes greening, but at other times when the ice is gone, you also lose the green areas. And she mentioned there the threat to emperor penguins. There was a mass breeding failure last year for some of those because of the loss of sea ice.
Yeah. I mean, well, that's why it's an emergency summit. It's very precarious out there.
How does it feel knowing that you're holding 1 million-year-old ice?
Quite terrifying, actually. Antarctica is a really key aspect of the global climate system because it is the only place that we will retrieve these long records of atmospheric conditions by drilling ice cores.
And this particular core, at best guess, we're really hoping it's more than 1.5 million years old. We look into the past to look at other time periods, other analogues for the climate and how it has changed before, so that we can use that information to better predict the future. So the previous oldest ice core we have goes back 800,000 years, which is a staggering timescale. But the motivation really for this new record is to extend that, and particularly over the last million years, because this is a really important time period when we think we went through quite a significant climate transition that we still can't explain. This new ice core, this Beyond Epoca oldest ice core, is a big European collaboration. The drillers successfully reached bedrock at 2.8 kilometres in January of this year. And just recently we have been taking shipment of these boxes. Here are the oldest ice sections, and this is what we're going to analyse. So we're looking at the section of core that spans the period from 700,000 years to the unknown age.
The drilling itself took place over 4 years, and before that there are 3 years or so of surveying to choose the exact location, to pinpoint the best location for drilling. In those 4 years, we're just there in the summertime, so we're there 3 months or so, trying to fit in as much drilling as we can per year to get that done. In the end, we drilled down to 2,800 metres, so that was done across the 4 seasons. The first season we had the setting up, drilling a pilot hole to just past 100 metres. The next year we come back, carry on down to 800, the following year down to 1,800, and then finally last year the team finished off going from 1,800 metres to 2,800 metres and getting that very oldest ice that we're so interested about.
So the ice cores are particularly powerful in understanding how the atmosphere has changed. And this is what really makes us so different from the marine sediments, for example. So marine records, they're fantastic. They can go back a lot further in time, maybe 5 million years in fact, but at a very, very low resolution. So perhaps 1 data point per 1,000 years. Whereas potentially within this particular ice core, we can actually extract enough information to look at the changes more on century to century timescales and understand the climate and the atmospheric changes all in one go. I'm a little bit nervous myself about holding it because it is so incredibly valuable. So many people have put their time and their careers and their effort into drilling this particular core.
There are a lot of things that can go wrong when you're drilling an ice core, but drilling was remarkably smooth. The drill we used for this project is very fast. It can drill up to 4.5 meters at a time, which doesn't sound like a lot when you're trying to get down to 2,800 meters, but it makes a big difference. We hang that drill on a wire and lower it into the hole. So we'll drill 4.5 meters, raise the drill up to the surface, pull that ice out, start processing it, logging it, packing it away, ready to come back to Europe, and then we'll send the drill down again. And we repeat that process over and over again. Now obviously the deeper you get in your drilling, the longer that process takes. So the season that I was there, we were drilling between 800 and 1,800 meters. It could take up to an hour just to lower the drill down to where we last got, another half hour to drill the next 4.5 or so meters, and then an hour to come up again. So at least 2.5 hours between sections. And so you can start to see how over 2,800 meters, it takes a long time to get this work done.
We're not analysing the full core, that's a huge amount of information. What we're really focusing on is just the very oldest part. And this particular core is from the very bottom part of the record. And at best guess, we're really hoping it's more than 1.5 million years old. So we're going to overlap with the previous oldest core and then extend back in time. And we have 190 meters to go through. So this bag here, this is a metre long section, so we've got 190 of these that we need to melt and analyse.
Yeah, so it is a lot of pressure having the oldest ice on Earth here. Yeah, it does keep me awake at night a little bit. The tricky thing with this type of analysis is that once it's melting, everything in the lab has to be ready to go and has to be calibrated and working.
and collecting good quality data. So the ice has to be kept really cold, because if it's not, then certain things in the ice can start to degrade. So to keep it in pristine condition, we have to keep it -20 or below, but we always keep it -25. And actually, a lot of the shipping logistics from Antarctica are even colder than that, so maybe -40. And that really preserves the samples in a really good condition. We load the ice onto our melt head, which is a gold-plated piece of metal which is heated. So the ice melts from below. In the center of that there is a hole which we have tubing. The tubing comes through to the lab. So it comes through the port from the freezer into the lab. It actually comes through this tubing here, which you can see is starting to get wet. All the interesting bit of the ice comes through this tube here. It goes through this part, which is the debubbler. So the debubbler separates the air that's trapped in the ice core from just obviously the liquid meltwater. It goes through these pumps and it goes to this part here, a splitter, and it splits off to 8 or so different instruments, and then it feeds the entire lab.
It's a full, complete, continuous record from the present day to as old as the oldest ice in this sample is. And we know it's at least 1.2 million years old at the bottom. Could be 1.5, it could be older, we won't know until we've finished the analyses. It's having that continuous record of what the climate was like on Earth and direct measurements. People often talk about the atmospheric air that gets trapped in ice cores. That's a very direct measurement, but the number of proxy measurements you can make are huge. There's the classics of looking at the isotopes of the elements in the water itself, in the water ice itself. They're an excellent proxy for what the temperatures were like in the areas around. You can look at ash that's come from major volcanic eruptions, the kind of eruptions that will cover the whole world in ash. You can see that in the ice. I've drilled samples of ice and you can see this little yellow band where this ash is stuck there. You can look at biology in the ice, stuff that's been microscopic phytoplankton that have been blown in from the sea and end up on the land. You can infer so many different things.
So interestingly, there's evidence from other archives, from marine records, that suggests that prior to 1 million years ago, our transitions from glacials to interglacial, so these are from extremely cold conditions to the relatively warm conditions we're experiencing today, there's evidence to suggest that they were much shorter, so about every 40,000 years. Whereas what we've seen more recently in our record is that these glaciations are lasting much longer, 100,000 years. And this is allowing big ice sheets to form over the northern hemisphere. And there doesn't seem to be much of an explanation as to why that transition occurred, why 1 million years ago we weren't having these 100,000 year cycles. And it's very relevant for today because at the time the evidence is suggesting that 1 million years ago our ice sheets maybe weren't as big. And that suggests that sea levels would have been higher. And there's also evidence that potentially the greenhouse gas concentration was also higher. So these are all analogues of how we think our future climate is headed. The way that the oceans and the atmosphere interact is we're all one big connected system. And Antarctica in terms of paleoclimate is so important. We want to understand what's going to happen in the future. And at the moment, our predictions are reliant on a very short observational period. What we do is we look into the past to look at other time periods, other analogues for the climate and how it has changed before, so that we can use that information to better predict the future.
The analysis showed that everywhere we looked for microplastics, we found them. And this is really important for us to understand globally, because Antarctica has been considered a remote location, somewhere that is separated from the rest of our planet, where us as humans live day to day. microplastics that we found during this study were mostly microfibers. And these fibers come from all forms of textiles. And it's not just our clothing, but also maybe our furniture and insulation, even in our wiring systems. Our results were suggestive that there are these multiple pathways that are bringing pollutants like microplastics into Antarctica. So really, if we're finding microplastics there, and we know that they've come in from multiple other places across the world, then I think it is a really important message for all of us that by only addressing plastic challenge together as a global community, are we going to get a reduction in these types of emissions?
We haven't seen an East Antarctic ice shelf collapse, at least in our lifetimes. For the last 20 years or so, since 2000, it's been losing a little bit here and there, but not much. But then right at the beginning of 2020 or so, it started sort of having itself every few months. One fast thing that happened was that weather event last week. I wouldn't say that it's the entire story, but it certainly added a pressure onto those ice shelves that we haven't seen before. And so that's why the timing was sort of interesting, I guess. 2 days, it basically was gone.
This is an ice shelf where there's been no ground-based research ever. So we're left to only see from our satellite observations and make our educated guesses at what's going on from there.
Even if the men die, there is still the opportunity that someone will find these negatives and understand the story. We've used the story of Shackleton to demonstrate the relationship between the evolution of photography, but also the evolution of the technology at the time. He was involved from the very outset with Captain Scott on the Discovery expedition, moving through to the Nimrod expedition, then of course the Endurance, and then ending with the Quest. In each of those expeditions, there is an evolution of photography and also perhaps an evolution of the way in which Shackleton recognises the power of photography. On the Discovery expedition, he is the first person in the world to actually take an aerial photograph of the continent. They are the very first images that show how the Great Barrier, the Great Ice Barrier, could be surmounted and showed the way forward for successive expeditions. On what was the Imperial Transantarctic Expedition led by Shackleton, which is otherwise known as the Endurance, the plan had been for Shackleton to cross from one side of Antarctica to the other, what was considered at the time during the heroic age of exploration as being the last great opportunity. Frank Hurley's story is a really interesting one. Hurley was instructed to document the entire journey. One of the nicknames that was given to Frank Hurley is a warrior with a camera. He was completely fearless. The most iconic images are the images taken during the polar night, showing the ship in profile. To set those images up, Hurley travels away from the ship. He set up a sequence of electric flares, and he has the flares charged and fired at exactly the right moment, So there would have been this extraordinary flash of light in otherwise complete sort of pitch darkness. To me, that image conveys the whole sense of the isolation of being in the Antarctic. Once the ship starts to show signs that it's going to be damaged and then mortally damaged by the conditions, Hurley takes on a role of what one could consider to be a true documentary photographer. At the point when the ship finally keels over, the pressure becomes too much and the ship is effectively crushed by the ice. He actually records the very poignant moment when the masts on the ship finally give way. He's at that point rescued probably about a quarter of the glass plate images that he's taken. Shackleton insists that the saved glass plate negatives are carried on the onward journey, despite the fact that each man can only take a couple of pounds of weight of personal effects. Even if the men die, there is still the opportunity that someone will find these negatives and understand the story. The image that shows them waving is a really important one. When that picture's taken, it is the men waving goodbye to the James Caird. When it comes back to the UK, because of the power of the picture, there are various versions of it where the image of the James Caird has been cut out and replaced with the image of the Yelcho, which is the rescue ship. It also demonstrates another aspect of creativity of what today we would consider to be Photoshop. Taken on the Quest expedition, Shackleton's final expedition, the use of the autochrome process to take some photos just demonstrates how far technology has expanded since the beginning of the Discovery expedition.
Autochromes were a very early colour process, which is fairly innovative and had not been used in polar exploration. They are based on 3 different colours of potato starch. To the back of that is attached a photographic emulsion. In 1920, Shackleton's planning his next expedition. He approached my grandfather, John Quiller Rowett, who he'd met at Dulwich College where they were at school together, and very magnanimously my grandfather steps in and says, "I'll fund the whole thing." They head down to South Georgia, and literally on arrival, Shackleton has a massive heart attack and dies. My grandfather broke the news to Lady Shackleton. She took a few days to think about it, but then said, "Our darling would prefer to be buried in South Georgia." There's very few things that remain. These glass plates are one of them. They've sat in a box for most of those 100 years, and this is the first time really they've been brought out. There's a couple in London before Quest departs. There's a couple in Madeira, in Funchal Harbour. Then there's some photographs on South Georgia of the countryside, of glacier. There is several of the building of the memorial cairn and the crew assembling at the cairn to pay their respects. My grandfather particularly wanted to see the output. You know, he invested in the technology that went into the expedition. You know, I think he'd think it's far beyond time that they've been put on display.
I think what draws people like Shackleton to go back to Antarctica is a combination of their expertise and their knowledge, but also this enormity of the alien landscape and the knowledge that actually we are specks as human beings in that environment.
Even on the Quest expedition, the men who'd been 2 or 3 times were saying, "We can't explain it. It's under the skin, and it just draws you back. You know, it's just a magnetic place."